Okay. So how do we write correct software? If you guys read Hacker News or Reddit, the answer is simple. You just use Haskell. But Haskell is really so 2015. If you ask people now, it's also very easy. You just need to use Idris. Um, Now, in this talk, we'll try to understand the difficulty of writing correct programs. Understanding a problem thoroughly is a prerequisite to finding solutions. And as we'll see, this problem is very, very hard. But without it, there is no computation. My name is Ron Pressler. I'm the founder of a company called Parallel Universe. And in the past year, I spent a considerable amount of time working on formally specifying and verifying complex distributed algorithms, which is how I became interested in this problem. The story of theoretical computer science begins about 100 years ago. With the growing success of mathematical logic, the mathematician David Hilbert laid out a program to formalize all of math. He wanted to prove the formalism consistent and complete, and to find a decision procedure, an algorithm, for determining the truth of every formal statement. Hilbert believed that anything that can be formally reasoned can also be fully understood. And by that I mean all of its properties formally proven. The 19th century view on the limits of knowledge was expressed by the maxim ignoramus et ignorabimus, meaning we do not know and we will not know. But for his retirement in 1930, Hilbert gave a lecture in which he challenged this view. He said, "For the mathematician, there is no ignorabimus, and in my opinion, not at all for natural science either. The true reason why no one has succeeded in finding an unsolvable problem is, in my opinion, that there is no unsolvable problem. In contrast to the foolish ignorabimus, our credo avers, we must know, we shall know." And those words are written on his tombstone, but unbeknownst to him, his program actually had been demolished one day earlier when Kurt Gödel tentatively announced his first incompleteness result. Gödel's incompleteness theorem demolished the first two pillars of Hilbert's program. And in 1936, Church and Turing broke the third, that of the decision problem, with proofs of what is today known as the halting theorem. The halting theorem, which is computer science's first ever theorem, was proven in both Church's and Turing's papers in 1936. But the theorem is so fundamental to the essence of computation that it's no accident that it appeared right alongside both definitions. You define computation and halting ensues. It basically says that there can't exist an algorithm that decides whether any given program ever terminates. The proof, which is given here in a very shortened form, is based on the idea of diagonalization or self-reference. So we assume such an algorithm H does exist, and if it does, then we can easily construct a program G that inverts the result of H, and then we do diagonalization, we pass G to itself, and we get a contradiction between what G does and what H says it does. If H says that it never stops, then we stop. If H says it does stop, so we loop forever. Therefore, there are no solutions to the halting problem. Now, this theorem has some immediate corollaries that tie it more directly to the problem of software verification. The first is a simple result about reachability. There is no algorithm to determine whether a program starting in one of a set of initial states ever reaches a certain state. And the proof is a simple reduction from halting. A more interesting corollary is Rice's theorem. Now, programs can compute what's known as partial functions. If they stop, given some input, we consider the output that they write on the tape to be mapped to the initial input. That's the function. If they never stop for a given input, we consider that input unmapped. So that's the partial bit. So Rice's theorem says that for any non-trivial property of partial functions, and by that he means any property that isn't true for all partial functions or for none of them. So for any property, we cannot write an algorithm to decide whether a program computes a function with a property. So for example, there's no algorithm to determine whether the output of a program is always the square of its input. And this theorem is also proven by reduction from halting. But for our purposes, I think that the most interesting corollary of the halting theorem is what we'll call the busy beaver theorem. And I think it's the most important because it captures best the notion of the complexity of analyzing programs, giving it some quantitative measure. And also because this result applies to both dynamic and static views of programs, namely their behavior as they run or their global properties, which we can maybe prove using logic. So it helps to demonstrate that those two views are really two sides of the same coin. In the dynamic version, let's define the following function on the natural numbers. The maximum number of steps a halting Turing machine with n control states may take before halting. Control states, that's basically the program for the Turing machine, and it basically says a program of size n. This function is well defined because there's only a finite number of Turing machines of size n. A subset of them terminates. We count the number of states for those subsets, and that's the function. And the theorem says that this function is not computable. The proof of that is simple. We say, let's suppose that it were computable. And if so, we could do the following. You give me a Turing machine. I count the number of control states it has, the size of a program. I compute f of n, because our assumption says that f is computable. I get a number, and then I run your program up to that number of steps. And if it doesn't terminate by then, I know it never terminates, because that's the definition of f. And we get a decision procedure for halting. There is no decision procedure for halting. Therefore, f is not computable. Now, not only is f not computable, any function that is known to be greater than f for all of n is also non-computable, because that would give us a lower bound, an upper bound on the number of steps a halting machine takes, and we can apply the same procedure and solve halting. So f is greater than all computable functions. The very same argument applies to the static view of programs. Now, to understand this result, first you need to know that for any given logical theory with a finite set of axioms, we can write a program that takes those axioms and starts applying deduction rules one by one, and therefore enumerates all theorems. Of course, it never finishes because it could be an infinite number, but we can start doing that. So this time, we'll define the function g of n to be the maximum size of a minimal proof of termination for a halting machine of size n. So again, there's only a finite number of machines of size n. A subset of them terminates. Each of them has at least one proof of termination, because if they terminate, the terminating trace of the program itself can be used as a proof. So each of them has at least one proof of termination. There may be a smaller one. So for each of them, we take the smallest proof. We take the maximum over all the terminating ones, and that's g of n. So by the very same idea, if g of n were computable, then if you give me a machine of size n, I just compute g of n, get a number, and then I use the description of that machine as a set of axioms, and I start enumerating proofs. Because g of n is finite, eventually I'll enumerate all proofs up to that size, and if none of them is a proof of termination of the program, I know that the program never terminates by the definition of g, and I have a procedure for deciding halting, which is impossible. Therefore, g is also non-computable. So this corollary of the halting theorem captures this fact. There is no computable function tying the size of a program to the difficulty of proving that it terminates, regardless of whether we're interested in a dynamic proof technique or a static proof technique. By the way, while we can't compute f for all of n, because that's what we just proved, we can compute it, or lower bounds for it, for some values. So for n equals 6, a program just 6 instructions, assuming a 2-symbol alphabet for the Turing machine, f of n is greater than 7.4 times 10 to the 36,000. That's the difficulty of showing a program of 6 Turing instructions terminates. Now, another question we may ask is this. So now we know that we can't come up with an algorithm to decide whether any arbitrary program halts, but are there specific programs that we know of that we can't tell whether they halt or not, even if we tailor a decision procedure just for them? Well, it turns out that as a result of Gödel's second incompleteness theorem, such a program should exist. We just didn't know how big or small it would be. And just a couple of months ago, a Turing machine with less than 2,000 control states was found that cannot be proven to ever halt or not. So that Turing machine would comfortably fit in a 4K challenge. It's comparable to a Python program of about 100 or 200 lines. And the result can actually be improved further. So this means that there are very small programs, 100 lines of Python, whose behavior cannot be proven by math. And I don't mean that the proof is too long or laborious to be feasible. I mean that mathematics is not powerful enough to ever prove the behavior of that small Python program, even in theory. So in any event, with the work of Gödel, Church, and Turing, Hilbert's program, at least as originally planned, was laid to rest 80 years ago by simple, compact mathematical objects that can be formally reasoned about, but not fully understood. Those are computer programs. The Church-Turing thesis, as it is presented today, is the conjecture that any computation done by any realizable physical process in the universe can be computed by the universal computational models described by Church and Turing. So in a sense, this means that anything in the universe could be formalized and simulated as a computer program. Now, as mathematics, as an academic discipline, not as a tool, is concerned with what's inside that small circle, and computer science is mostly concerned with what's outside it. And actually, as we'll see right away, even those programs that do lie within the small circle, almost all of them, or certainly most of them, are only provable in principle, not in practice. So I think it's safe to say that computer science isn't math. This actually was said by Turing, but we'll get to that. All right. So whether verification, halting and corollaries, is decidable or not doesn't quite capture the difficulty of the problem. Because Turing machines can have infinite behavior, the problem of verifying them could, in a sense, be considered similar to the problem of sorting an arbitrary list of either finite or infinite length, or finding the maximum element in such a list of finite or infinite length. So both of them are equally impossible. But we know that when we restrict finding the maximum element or sorting to the finite case, their difficulty is very different. So let's try to figure out how hard verification is. So it took another 30 years for the issue of algorithmic difficulty to be properly defined. The theory of computational complexity was born in 1965 in a paper by Juris Hartmanis and Richard Stearns, which begins so. In his celebrated paper, Turing investigated the computability of sequences, functions, by mechanical procedures, and showed that the set of sequences can be partitioned into computable and non-computable sequences. One finds, however, that some computable sequences are very easy to compute, whereas other computable sequences seem to have an inherent complexity that makes them difficult to compute. Now, in his 1993 Turing Award lecture, Hartmanis says that he viewed complexity, he liked physics, he viewed complexity as a law of nature. And he said it's a law of nature just like in physics. Now, before we go on, it's absolutely crucial to understand that complexity theory is concerned with the inherent complexity, the difficulty of problems, not in analyzing the complexity of specific algorithms or a solution. So the complexity results, they provide bounds for any algorithm, known or unknown, for solving a problem. One more thing we need to make clear is that questions of quantum computing aside, it's important to understand that complexity results apply to humans, or at least we've never encountered any human violating any complexity bound. Okay, so it was no surprise, I think, that it was our very same question on the precise difficulty of the halting problem that allowed Hartmanis and Stearns to show the inherent difficulty of some problems and prove what is now known as the time hierarchy theorem, which I think is the second most important theorem in computer science, which basically says that computational problems form an infinite proper hierarchy of difficulty. So the problem, as I'll present it here, is sometimes known as bounded halting, and it asks the following. What is the complexity of deciding whether a program M stops an input X within n steps? So if we just simulate the program and we run it, and assuming that our simulation procedure has a low overhead, we can certainly do it in less than an order of n. But can we do it faster? So let's assume that we can, and that we have, so given some n, we have a program h of n that does exactly that, and it runs, so it answers whether m halts or x on x within n steps, but it does so faster than n. For the sake of this proof, we need to do n minus 2. You'll see why. By the way, this is an approximate proof. It's more similar to proofs by Cook on RAM machines rather than Turing machines. But anyways, we take the exact same proof of the halting theorem. We use diagonalization. We define G, which inverts HN's result, and we pass G to itself, and we get a contradiction, because if H of n says that G running on G does not stop within n steps, it completes doing that in n minus 2 steps, and then it takes us just one more step to return true, and we have finished in within n steps, and we get a contradiction. The same thing the other branch. So the complexity of this problem is an order of n. We can't do it any faster. So put simply, you can't know what a program will do any faster than actually running it. An interesting question is, can we generalize from one input to another? So this is for a particular input x. Can we work really hard, much bigger than n, 2 to the n, on some inputs, so that later on we'll be fast on all other inputs? Like study the state space of the program and then give fast answers for the rest of the inputs. So I call that amortized bound halting. Unfortunately, I can't show the proof. It's an immediate corollary of bound halting, and the answer is no. So this result actually answers a question on the complexity of the halting problem. Because we can't answer any question about a program faster than running it, as soon as a program reaches a state that it's visited before, and again, neglecting the overhead of actually writing down which states we visited, we can immediately tell the program never halts. So in the worst case, the complexity is at least the number of states of the program. And if we're talking about Turing machines, so I'm not talking about the control states, the states of the program, including the tape. So in the general case, so this is the complexity of the halting problem. In the general case, a Turing machine can have an infinite number of states. So the worst case complexity is infinite, and we get the undecidability of the general halting problem as a special case of bounded halting. This is a more general theorem. And as we'll see, and this is the interesting bit, this result is extremely robust. It holds even if we strip away the computational power of our machines from Turing completeness to pretty much anything else. This holds for any computational model, almost. Another question is, so far we've talked about Turing machines, which is really a very general object, and it's a computational model. It's not really a programming model. In practice, we write our programs in nice programming languages with abstractions, maybe even semantics. So can we exploit the language semantics to answer the question faster? So we'll address this question head on later. Spoiler alert, no. Okay. Before we go on, I'd like to state the verification problem in the most general way, the holy grail of verification. What we want we want most if we can have it. So what we really like is, given a program M and a statement phi and some logic that can talk about the properties of M, we'd like to know whether M satisfies phi. So it's easy to see that this very general problem contains within itself halting and Rice and reachability and all that, so it certainly can't be easier. Now, in mathematical logic, if M satisfies phi, we say that M is a model for phi. So we need to check whether M is a model for phi. So this problem is actually known in literature as the model checking problem. Not to be confused with model checkers. There are specific algorithms for solving the model checking problem. So how we determine whether M is a model for phi or not is up to us. we can use deductive proofs if you want. We can use types, whatever we want. The results, the computational complexity bounds that I've shown, and I will show more, applies to all of them. So no specific algorithm can be faster than the general case, the general complexity bounds. And again, the results apply both to machines and humans. So to try to tackle the verification problem, let's start restricting our machines. So one way to do it is to restrict ourselves to programs that are easily proven to halt. How do we do that? We can write them in a style or even in a language that does it for us that requires that all loops or recursive calls have a counter that is decremented with every call. So these languages are called total languages, and they allow writing a useful subset of all total programs. But if we look at our diagonalization proof for bounded halting, we see that even if Hn could only accept programs M that were written in total languages, Hn itself would still be able to be written in that total language because it only needs to run for up to n-2 steps, so we can have a counter. The same thing goes for G. G would also be written in that language, so we are allowed to pass G to H, and the same result holds. There's absolutely no change. So verification is still the order of the number of states of the program. Total languages make no difference. We can still ask, what is the relationship between the program size and its number of states in total languages? Before, we've shown that for general Turing machines, it's non-computable. I'm sorry to say I'm not exactly sure about the precise answer. I do know that it must be greater than all primitive recursive functions, and it's definitely greater than the Ackermann function, but it may still be computable. In any event, for our purposes, it's still as good as infinite, and total languages actually don't help verification at all. Now, this 10-line Java or C example is written in this total style. All loops have decrementing counters, and it clearly always terminates. It also doesn't do any tricky mathematical operations, just addition and subtraction. Yet mathematicians have tried to prove this program never crashes, never reaches that line there, for 270 years. And that's because this program crashes if and only if Goldbach's conjecture is false. Actually, for 32-bit integers, we know that it never crashes because we tried all of them, but we don't know the answer for, yeah, I think we know up to 10 to the 14. We don't know for 64 bits. There are other ways we could restrict our computational model. There are languages that only allow writing programs that run in polynomial time. Another model is pushdown automata, which is very interesting in itself. But we will jump directly to finite state machines, the weakest computational model that's still useful, because there we can find the most interesting results. So automated methods for full verification of finite state machines, called model checkers, have existed since the 80s, and they're probably the most common form of formal verification techniques used in the industry. And it is precisely because practical automated methods exist that the complexity of the problem has been studied extensively. Again, the results I'm going to present are about the inherent complexity of the model checking problem, not for specific model checkers. They apply to any proving mechanism, human, automated, etc. And these are the complexity bounds for two different logics that can be used to describe the properties of the property phi. And you'll see that if we treat phi as a constant, then the same result applies to finite state machines. It's the order of the number of states. But the familiar complexity classes are sometimes too crude. We talk about worst case, and sometimes the real life cases are easier. So parameterized complexity is a theory, relatively recent, that tries to address this problem in some cases by introducing finer complexity classes. Perhaps the most important of them is FPT, fixed parameter tractable, which says that a problem may be intractable, for example, exponential or more, in some parameter k, which is a function of the input, but it is otherwise polynomial in the size of the input. So if in real life the parameter k can be kept small, then the problem would still be tractable, even though it is intractable in the worst case. So an example of a problem in FPT is SAT, Boolean formula satisfiability. We write a Boolean formula, and we want to know whether there's an assignment to the variables which is true. So this problem is the quintessential NP-complete problem, but even the naive algorithm that tries all assignments is only exponential in the number of variables, and that's the parameter k. Otherwise, it is linear in the length of the formula. Another example is the Hindley-Milner type inference, which is why it is efficient in practice. So Hindley-Milner is FPT, and that's why for most programs it is linear. So a 2005 paper explores this question, and they try to parameterize verification complexity by modularizing programs. So the idea is that maybe each module or component of the program could be verified in isolation, and then we'd put them together and verifying the composition of component, while maybe intractable in the number of components, but that number would be low, like 5, 10, or 50. It would be tractable in each component's size. And if that were so, we could basically compose programs from smaller modules, prove each of them in isolation, then combine a small number of them, and we have efficient verification. But the result is negative. And the proof actually is very cool. The authors note that k finite state machines can actually simulate any non-deterministic Turing machine with k tape squares. And that problem is known not to be an FPT. Actually, it's pretty high in the hierarchy. It's very non-decomposable. So verification is not tractable even in the parameterized sense of being FPT, and we do not think the difficulty can be solved by considering other ways of treating k as a parameter. So this 2005 result is pretty profound. It is proof that we cannot, in general, decrease the effort of proving a program's correctness using modularization. Correctness does not decompose. Okay. So now we finally get to the question of language. Usually we don't write our programs by drawing huge state transition diagrams. We use nice programming languages with nice abstractions, like I said, maybe even proper semantics, and we write programs that are, in general, very succinct compared to their state space. So can we exploit the structure in the source code? And that question is known as the symbolic model checking problem, and Philippe Schnobelin, who also wrote the previous paper I showed you, who studies the computational complexity of verification, writes that from a complexity theoretic viewpoint, there is no reason why symbolic model checking could not be solved more efficiently, even in the worst case. So there's hope there. Symbolic model checkers only deal with a very special kind of huge structures. The structures are the transition diagrams. Those then have a succinct representation. Okay, so the result is that restricting ourselves to programs that have a succinct representation does not help at all. The problem is p-space complete for finite state machines, and it happens to be an order of the number of states. We cannot reduce that bound, which is, so p-space complete for finite state machines is the same as simply expanding the state diagram of the program and forgetting about the code. Indeed, it's not only the worst case. This has been observed in many instances from reachability to equivalence, and can now be called an empirical fact. It's not only the worst case. By the way, if you see the Kripke structures there, that's the abstract transition graph. It's just a way of talking about programs in the verification community without talking about source code representation. Just as a quick example to give you intuition for why verifying finite state machines is so hard. So consider a programming language that has nothing but Boolean variables and function calls. There are no higher order functions, no recursion, and no iteration at all. So such a language would clearly only describe finite state machines. By that I mean that it's easy to tell from the source code how many states there are. That's what I call a finite state machine program. So you can see over here, A equals B equals C, etc. No loops, no recursion, no higher order functions. In the end there we have 6 Boolean variables. They're all tried once with true, once with false. So we have 2 to the 6 number of states. So yet verifying this not even useful language is still p-space hard. Because this trivial program, you can write a program like this, and it directly encodes this problem of determining whether this predicate calculus formula is true or false. It's known as a TQBF problem, true quantified Boolean formula, and it is p-space complete. Again, it's a quintessential p-space complete problem. And unlike stat solvers that, for some magical way, work, we don't have good solutions for that. So I think that in light of all these results, we can state this informal theorem. There does not exist a generally useful programming language where every program is feasibly verifiable, and there cannot exist one. Okay. So now we know why writing correct software is hard, because it has to be. But while we can't verify all programs all the time, regardless of how they're written, there's nothing stopping us from verifying some programs some of the time for some properties. Now, Turing understood full well the difficulty in writing correct software. In a lecture to the London Mathematical Society in 1947, he said, "The machine interprets whatever it is told in a quite definite manner without any sense of humor or sense of proportion. Unless in communicating with it, one says exactly what one means, trouble is bound to result." And he has a solution. What was Turing's solution? Types. We shall need a number of efficient librarian types to keep us in order. So I mostly mention types because I imagine that they're popular in this crowd that's interested in programming languages. I also want to talk about deductive proofs and model checkers. Sadly, there's not enough time. But as a motivation for discussing types, I want to ask the following question. This is Rice's theorem again. And yet, not only is it possible, but it's actually quite easy. It takes no effort on our part to ensure that, say, a C or a Java or a Haskell program returns an int. How is that possible? Any ideas? Anyone? Just shout. Yes, but why? Yes. No, but how? But Rice's theorem says it's impossible. How is it possible? Okay, all right. So some people, that has to do with it, right? Some people, I was hoping to hear that answer. They seem to assume that. Does anyone think by construction? No, good. All right, so some people think, and you see it's if you read Reddit and Hacker News, that there is no violation because the property is correct by construction. This is absolutely false. Rice's theorem says absolutely nothing about construction.
Is it a trivial property?
Yeah. So it doesn't say anything right about construction for good reason, and that is because if we could prove things by construction, then we'd have the following efficient verification problem. I would write my program in Python, and then because it's so easy, you translate it to Haskell or Idris, and voila, problem solved. So this is impossible because the complexity applies also to humans. So the real answer must directly address Rice's theorem. So a property would either need to be trivial, or it may not be a property of a Turing machine. The partial function will not be computed by a Turing machine. So in the case of an integer, what the type means, and you said correctly, is that either the program never terminates or it returns an integer. But this is true for every program, because every program either never terminates or returns something, and that something can be interpreted as an integer. So not even a single bit of information is given to us. Now, some of you would recognize that this is not always the case. So, for example, in Haskell, you can relatively easily show that a program returns a string of numeric digits. So this specifies a lot of bits, because we restrict every byte to 10 out of 256 possible outcomes. So how is that not a violation of Rice's theorem? This one is clearly not trivial. Well, that's because the property is not generated by a Turing machine, but by a very small finite state machine, as I'll now show. Before that, we should say a few words. I wish I could talk about this more, about abstract interpretation, which is an elegant and mathematically very deep solution to verification, which was introduced in the 70s. And tools that employ it are usually called static analysis tools. This technique is fully automatic, and it avoids the intractable complexity bounds by being imprecise. So the very rough idea is to consider, so given a program that we want to verify, we consider another program that is a sound but less precise abstraction of our input program. And that abstract program would be a small finite state machine, and then we could model check that. So the complexity would be an order of the number of states of the abstract program. So for example, in this program on the left, this program has an infinite number of states. But if we only care about the parity of x, just a second, we can abstract that program to this small finite state machine program, and we still know x's parity in 2 out of the 4 labels, in P2 and P3. Yes? What is it? The narrowing here? Well, we'll discuss. That's a technical. I'll discuss that with you later. Let's not get too technical here. This is an introduction to types. Anyways, so one of the several ways of looking at types is as an abstract interpretation. So we in the concrete program we have a variable x of type int that can take the values 1, 2, etc. And we abstract all of them as the value called int in the abstract program. So the values of the abstract program are the names of the types in the program. So how many states does the abstraction have? It's about as many as there are concrete types in the concrete program or the particular chain of function application. So every state in the abstract program would be the name of the function we're currently evaluating, and it's either input or output type. So maybe it's the number of concrete types times the number of functions, depending on the structure of the program. Now, the number of concrete types can be greater than the number of types that we actually spell out, because people write programs with generic types and polymorphic functions. But this is not a problem, because just like we can have a concrete function that takes 3 and returns 5, the abstract program can take int as a value and return list of int as a result. So using nothing but our result of bounded halting, namely that the complexity of verification is in the order of number of states, and now that we understand abstract interpretation and the relationship to types, we can immediately obtain our bounds for type inference algorithms. So the lower bound for type inference algorithms is the number of concrete types in the program. So in a program, and we got that result using nothing but the halting theorem, right? So in a programming language without dependent types, if you don't know what those are, so it's not important. So that number is relatively small, and the result what we get is a finite state machine. And the types don't express properties of programs; they express properties of a finite state machine. So that's why there's no contradiction with Rice's theorem. And in fact, you can take any Haskell program, remove all the function bodies, replace them with functions that are finite state machines. You get a program that's completely wrong, but it would still type check. So for any Haskell program, there's a finite state machine Haskell program that type check completely, and it is completely wrong. On the other hand, in languages with dependent types, so the number of concrete types can be infinite, and therefore type inference, which is still the order of number of states, is of infinite complexity, and therefore it's undecidable, and it's really as simple as that. All right. So in his follow-up to his very famous article, No Silver Bullet, where he argued that we'll never again see another order of magnitude increase in programmer productivity, he wrote that in '84, and he was right, so far at least. Fred Burks writes, is Einstein's statement that nothing can travel faster than the speed of light bleak or gloomy? The very nature of software makes it unlikely that there will ever be any silver bullets. Okay, so now we have proof of that, but what can we do? So we've seen that computer science studies objects, computer programs, that are composed of very basic components, be they beta reductions in lambda calculus or Turing machine instructions, that on their own, each of them is easily subject to full mathematical reasoning. But it is their interaction that is essentially intractable. Now, I think this is similar to physics, where, for example, the gravity equation is very simple. And that equation composes beautifully. You can have multiple instances of it for multiple bodies. It's all very equational reasoning. Everything composes. But still, more than one instance of the equation, more than two gravitational bodies in gravitational interaction, the problem is already chaotic and there's no closed form solution. So I think we should take a page out of physics' book and embrace empiricism. So let's consider the verification problem again. We must restrict either the left-hand side or the right-hand side. So I hope that by now it's clear that we'll never find a generally useful category of programs for which verification is always affordable. But we can make the following obvious observation. All programs we care about are created by people. And if you like, we can consider humanity to be one large Turing machine that generates all machines M. And it is very likely, in fact, we know it to be the case, that there are patterns in those machines that humanity generates. And if we study them, we would be able to maybe get some affordable verification. Now, we can't analyze humanity as a program. The only viable method is empirical study of the programs humans write. And I think we should begin with a taxonomy of program types, size, cost, etc. Now, this observation also makes some useful restrictions on the right-hand side possible. So far, all the properties we've seen, like halting, reachability, were global ones. But in practice, we know, and we know that empirically, that some local properties are also very useful to prove. A great example of that is memory safety, which is known to be a source of very common, and very costly bugs. And we may be able to find other useful local properties. But this, too, would require empirical study. A great place to start would be a taxonomy of bugs by cause, prevalence, association with program types, and maybe most importantly, cost. Such empirical studies would require the cooperation of academia and industry. With that empirical knowledge in hand, we'll be able to tackle the interesting special cases using ad hoc mathematical techniques, just as physics does, simplifying assumptions, heuristics, approximations, etc. One such really beautiful example of empirical research is a recent study at the University of Toronto that discovered that a vast majority of catastrophic failures in large distributed systems is due to programmers not thinking enough about error handling code. The code is there, they just don't put much thought into it. And this is clearly a psychological effect. Now, I'm not saying that computer science is physics. Juris Hartmanis actually wrote a paper explaining why it isn't physics, and obviously it isn't math. But he says that computer science differs from the known sciences so deeply that it has to be viewed as a new species among the sciences. I'll conclude with something Fred Brooks wrote. Complexity is the business we are in, and complexity is what limits us. Some people seem to be philosophically offended by this notion, and they try to fight the proven limitation. They are under the impression that the world, and now I'm not just talking about computation, is essentially simple, and it is stupidity of people and institutions that needlessly complicate it. And if we were only to apply careful mathematical reasoning, we could find solutions to anything. Now, computer science is the very discipline that proved that essential complexity arises even in the smallest of systems. Some of them are unfeasibly proven, and some of them just are beyond the power of math, even small 100-line programs. Yet sometimes it is computer scientists, and I think more software developers, who attempt to challenge the very foundation of their own discipline. Complexity is essential, it cannot be tamed, and there is no one big answer. The best we can do in society as in computing is to apply lots of ad hoc techniques and, of course, try to learn about the particular nature of problems as much as possible. Thank you. Yeah, time for questions? Anyone? You first. Oh, no, we do. The question is how it's related to our business. No, it's kind of tangential, but we had to use some of our algorithms were too complicated to just write and debug, and we had to use formal methods. So we're using formal methods pretty much all the time, and that's how I got interested in the topic. Yeah. With the what? Four color, yeah.
One question is like you said, well, programming is not mathematics because there are all these things that cannot be formalized and proved.
They can be formalized. They can't be proven. Yeah.
But it seems that the discussion on this problem is that this problem involves computers to prove something, and therefore it is sort of empiric.
It is what?
Sort of empiric.
Okay.
Observation.
But the four-color theorem is kind of going the other way around. It's starting with math, which is a lot simpler than computer science or physics, and applying techniques that have been studied in computer science and also in math to solve a mathematical problem.
So it seems that one way of seeing this is that it sort of stretches the definition of mathematics itself. Isn't it the case that computer science also sort of stretches that?
Well, if you want to axiomatically call computer science, if you want to call computer science math, then yes. Actually, I think I have something nice here that Paul Cockshott, he's a computer scientist and political economist at the University of Glasgow, and he said that actually something very similar to what you were implying. Turing's 1936 paper in the computable real numbers marks the epistemological break between idealism and materialism in mathematics. Prior to Turing, it was hard to get away from the idea that through mathematical reason, the human mind gained access to a higher domain of Platonic truth. Turing's first proposal for a universal computing machine is based on an implicit rejection of this view. His machine intended to model what a human mathematician does when calculating or reasoning, and by showing what limits this machine encounters, he identifies constraints which bind mathematical reasoning in general, whether done by humans or machines. Turing starts a philosophical tradition of grounding mathematics in the material, and hence ultimately on what can be allowed by the laws of physics. The truth of mathematics become truths like those of any other science, statements about sets of possible configurations of matter. Now, so I don't know if I necessarily agree that mathematics has changed in that way, but it's certainly different. So I wouldn't call that math, but if you want to call that math, so now math is different.
Sort of accepted that for Turing is part of math basically because mathematicians accept it.
Yeah, yes. There's a social math is whatever mathematicians do. Yeah. Okay. Anyone? Yeah.
So you mentioned you're using formal methods, and in your experience, what is the relation between the size of the specification and the size of the actual algorithm you're using to verify?
Yeah. So we're using TLA Plus. The entire program is well over 50,000 lines of code, maybe even 100,000. Specification is about 1,000 lines, 1,500, with 3 different refinement levels. So there's at least a 10x, if not 100x difference between the size of the formal specification and the actual algorithm. And it's TLA Plus actually specifically scales very nicely to very, very large real-world systems, and it's also very easy to learn, which is basically why we adopted it.
Come back to the naked when you show
The-
the verified problem.
The Venn diagram.
Yeah, that is some reason for the not the verified. Yeah, the proven be less than
Yes, that's because of Gödel, Church, and Turing. They showed that Hilbert thought that they're equal,
Yeah.
and
No. So this is inside, but the one that are not formally reasoned be much more than the one.
why is it bigger?
Yeah. There are more.
There are more things that cannot be proven than things that can.
Yeah.
There's actually a simple cardinality argument why that must be so, but everything that can be proven formally must be formally reasoned, at least. So the formally reasoned must contain the proven, because
I know that the ones that are no, yeah, that are outside the.
completely outside.
Yeah.
Yeah, I don't know about. Are there things in physics? So the Church-Turing thesis basically says that there is nothing outside. In a way you can think about it. But that's a conjecture, a hypothesis. We don't know if it's true. So far we haven't found anything. But so far anything we know in the universe would fit as a computer program, simulated as a computer program. Yes.
On your experience, well, I mean, you said like the proof, sorry, specification can be like 100 times less. But how harder is to write it? For example, if I write a program for 1 week, how much time it takes to write the formal specification?
It's kind of hard to say, because the whole idea of formal specifications is that's the part where you think. So once you think about the program and you think and you write it down and you reason about it formally, then it's very easy to write it afterwards. If you just write it, supposedly you also need to put in the same amount of thinking. In practice, you don't, so you postpone some of the thinking later to debugging, which is fine, by the way. It's a valid technique. But you can also do debugging on your formal specs. It's actually very nice. It gives you counter examples. So on the whole, it definitely saves time. But it depends. If you want to do formal proofs, deductive proofs, then that would be very expensive. But if you use model checkers and other automated techniques, some maybe automatic proofs, then actually it is very affordable and it's faster for some problems. Now, if you want to write a very, very simple program, then I wouldn't use formal methods. But for stuff that you say, okay, this can be subtle, or certainly for distributed algorithms or anything concurrent, and it turns out to be easier. But it depends also on the tool you choose. Some tools are easier to use than others. Yes.
You mentioned using empiricism on certain parts of periodic reasoning like, do you think that that's something that a machine could do, like machine learning?
Sure. So the question is whether the machines could do the empirical studies. Of course. If we have machines that gather statistics, and machine learning is basically statistical algorithm clustering. That's what they do. So if we could use machines to study all of GitHub, and some people are already starting to do that. So people are working in that direction. It's just that I sense a little bit of a slight disrespect among people in programming language research towards those empirical programs, empirical studies. But that is absolutely essential, because otherwise you're not focusing your solutions, and you must, because there is no general solution to simple proof. Anything else? All right. So thank you very much. Does exist. And if it does, then we can easily construct a program G that inverts the result of H. And then we do diagonalization. We pass G to itself, and we get a contradiction between what G does and what H says it does. If H says that it never stops, then we stop. If H says it does stop, so we loop forever. Therefore, there are no solutions to the halting problem. Now, this theorem has some immediate corollaries that tie it more directly to the problem of software verification. The first is a simple result about reachability. There is no algorithm to determine whether a program starting in one of a set of initial states ever reaches a certain state. And the proof is a simple reduction from halting. A more interesting corollary is Rice's theorem. Now, programs can compute what's known as partial functions. If they stop, given some input, we consider the output that they write on the tape to be mapped to the initial input. That's the function. If they never, but unbeknownst to him, his program actually had been demolished 1 day earlier when Kurt Gödel tentatively announced his first incompleteness result. Gödel's incompleteness theorem demolished the first two pillars of Hilbert's program. And in 1936, Church and Turing broke the third, that of the decision problem, with proofs of what is today known as the halting theorem. The halting theorem, which is computer science's first ever theorem, was proven in both Church's and Turing's papers in 1936. But the theorem is so fundamental to the essence of computation that it's no accident that it appeared right alongside both definitions. You define computation, and halting ensues. It basically says that there can't exist an algorithm that decides whether any given program ever terminates. The proof, which is given here in a very shortened form, is based on the idea of diagonalization or self-reference. So we assume such an algorithm H Okay. So how do we write correct software? If you guys read Hacker News or Reddit, the answer is simple. You just use Haskell. But Haskell is really so 2015. If you ask people now, it's also very easy. You just need to use Idris. Now, in this talk, we'll try to understand the difficulty of writing correct programs. Understanding a problem thoroughly is a prerequisite to finding solutions. And as we'll see, this problem is very, very hard. But without it, there is no computation. My name is Ron Pressler. I'm the founder of a company called Parallel Universe. And in the past year, I spent a considerable amount of time working on formally specifying and verifying complex distributed algorithms, which is how I became interested in this problem. The story of theoretical computer science begins about 100 years ago. With the growing success of mathematical logic, the mathematician David Hilbert laid out a program to formalize all of math. He wanted to prove the formalism consistent and complete, and to find a decision procedure, an algorithm, for determining the truth of every formal statement. Hilbert believed that anything that can be formally reasoned can also be fully understood. And by that I mean all of its properties formally proven. The 19th century view on the limits of knowledge was expressed by the maxim ignoramus et ignorabimus, meaning we do not know and we will not know. But for his retirement in 1930, Hilbert gave a lecture in which he challenged this view. He said, for the mathematician, there is no ignorabimus, and in my opinion, not at all for natural science either. The true reason why no one has succeeded in finding an unsolvable problem is, in my opinion, that there is no unsolvable problem. In contrast to the foolish ignorabimus, our credo avers, we must know, we shall know. And those words are written on his tombstone.